Mercury. It's a really beautiful substance. It's the only metal that's a liquid at room temperature and pressure. It doesn't become a solid until it goes below minus 38 degrees Celsius. In its liquid state, the atoms have enough thermal energy to overcome the rigid metallic bonds that confine most metals to solid structures at room temperature. Because of this, the atoms have enough energy to jiggle about and flow past one another. And it's the third law of thermodynamics which links the temperature to the level of entropy in a system. So, as the temperature of a system reaches absolute zero, the level of entropy reaches its lowest possible value. When the mercury atoms in the liquid have enough thermal energy, they can break free from the surface in the form of a vapour. This vapour has a higher entropy state, meaning there are more ways in which the atoms can arrange themselves in the space around them. The less energy there is in a substance, the more ordered the atoms are within it. This is why when you cool a liquid, it turns into a solid. So if we use liquid nitrogen to take the temperature of the mercury down below its freezing point of minus 39 degrees Celsius, we know that we will also be reducing its entropy. Which means we'll be able to play around with it as a solid, say mould it into something like a hammer. At this point, mercury becomes more like many of the solids you may be familiar with at room temperature. It's much more rigid and less malleable. It forms a solid metal in which all the atoms are ordered in a regular crystalline structure, which means the atoms arrange themselves in a repeating pattern throughout the solid. But although the atoms are arranged in this solid crystalline structure, they're not completely motionless. A more precise phrasing of the third law would state, the entropy of a perfect crystal at absolute zero is exactly equal to zero. So we'd have to have a perfectly arranged crystal and remove absolutely all the thermal energy to reduce the entropy to zero. The problem is that the concept of absolute zero is a theoretical one. It's just not possible to completely remove all the thermal energy from within a substance. So it might seem strange to have absolute zero in our laws of thermodynamics, given that it's a theoretical temperature, but it provides us with an absolute scale with which we can link temperature and entropy. This in turn allows us to understand how temperature influences the behaviours of systems and materials in the world around us, which is pretty important when we study the climate or design anything from spacecraft to microwaves to mercury hammers.
Oh, it fell down.
Oh,
Fell down.
what happened? Were we filming?
Yep.
Brilliant.
It's like Terminator.